All right, here is section 10.3. In our learning targets for today, we're going to solve radical equations. Then we're going to identify some extraneous solutions. Now, an extraneous solution is a solution that doesn't actually work when I put it back into my original equation. And then the third thing we're going to do is we're going to solve some real-life problems involving radical equations. So here's my first core concept. So if two expressions are equal, then their squares are also equal. So if I have A equals B, then I know if I square both sides, they're also equal. So let's kind of look at that in practice. So here we're going to solve each equation. And remember that a radical is that thing underneath my radical sign, and I want to solve for my x. So the first thing I have to do is get that entire radical sign by itself. So I write my original equation, then I see to get this by itself, I have to subtract 5 from each side. So now I have the square root of x equals 8. So now to undo this square root, I have to square both sides. Because remember, undoing square roots, we can square them. So now I have x equals 64. So my solution would be x equals 64. So let's look at B. I have 3 minus the square root of x equals 0. First thing I always want to do is actually go back and double check to make sure that my answer works. And we'll see several occasions here in a little bit where this doesn't actually work, so it is important to go back and check your answers. So now let's look at part B. 3 minus the square root of x. Oops. So I first want to get the x all by itself on one side. So I add the square root of x to both sides, which gives me 3 equals the square root of x. Then to undo the square root, I square both sides, so I end up with x equals 9. So now let's put that back into my equation. So 3 minus the square root of x equals 0. I plug 9 back in. 3 minus 3 equals 0, and it works. So I know that both of those solutions are actually good solutions. So now I want you to try a couple and see how you can do. So now we have a little bit more complicated, right? There's some other things being done to my radical sign first. So again, the first thing I have to do is get this whole radical by itself. So I write out my original equation. Then the first thing I'm going to want to do is I want to subtract this 3 from both sides. So now I have 4 times the square root of x plus 2 equals 16. So now I'm going to go ahead and divide by that 4 to get the radical by itself. Now that the radical is by itself, now I square both sides. So I end up with x plus 2 equals 16. So now I can easily solve for x. I can get x all by itself by subtracting that 2 from both sides. So I get x equals 14. So again, I put this back into my equation. So 14 plus 2 is 16. So the square root of 16 is 4, and 4 times 4 is 16 plus 3 is 19. So my solution does work here. So now what do we do if I have this radical on both sides? Okay, so there's a couple of different methods. So first I write my equation out and I square each side of the equation, right? And then I can simplify. So I end up with 2x minus 1 equals x plus 4, and then I solve for x. So I subtract x from both sides and I add 5 to both sides, so x equals 5. So the second thing I can do is I can graph each equation, right? I can graph the square root of 2x minus 1, and I can graph the square root of x plus 4, and I can see where they meet. I can either use the intersect feature in my graphing calculator, or if I'm using Desmos, I can just click on it and it will show me that the intersection is at x equals 5. So I get the same solution no matter which way I do it. So now here I have a cube root of something, right? We've just been dealing with square roots so far. So now I'm going to be looking at this cube root. So I have the cube root of 5x minus 2 equals 12. So I see that the radical sign is the only thing that I have on this left-hand side, so I can go ahead and start simplifying and solving. So first I write my equation. Now, since this is all by itself, I go ahead and cube each side, right? Because I'm undoing the root. Since it's a cube root, I cube each side. So I have 5x minus 2 equals 1728. So then I can solve for x. So I'm going to add 2 to both sides and then divide by 5. So my x ends up being 346. So now here are a few that I want you to try. And remember, the first thing we always have to do is get the radical all by itself. So now I have two variables, right? I have a variable underneath the radical and I have a variable that's not underneath the radical. So how do I solve for this one? So I kind of go along the same steps that I've done. I write my equation, and I see that the radical is the only thing on the right-hand side, so I go ahead and square both sides. So I end up with x squared equals x plus 6. So now here you've seen several of these, right? This is just a simple quadratic. So now I want to get everything to one side. So I have x squared minus x minus 6 equals 0. And so now I'm solving a quadratic. Okay, and I would look at this one and say, oh, let's try and factor this one because my a value is 1. So if I can factor this, which I can, right, I end up with x minus 3 and x plus 2 equals 0. So then I do use my zero product property, set them both equal to 0, and I solve for x. So I have x equals 3 or x equals negative 2. So now I have to go back in and try both of my answers, both of my solutions here back in my original equation. Okay, so I plug in my x's that I found. So I found 3 and I found negative 2, and I try it again. So does 3 equal the square root of 9? And does negative 2 equal the square root of 4? So 3 does equal the square root of 9, so that one works. This one does not work because I ended up with a negative on the other side. So I know that that solution is not actually valid. So that's what we call an extraneous solution, because when I went through and solved it, it worked, but when I plugged it back into the original equation, it did not. So my only real solution for this one is x equals 3. So now here's another one I want you to work on solving. So let's try this. So again, I see I've got several things being done to my radical, and let's undo those. So I write my original equation, then I subtract 13 from both sides, right, to get the radical by itself. So now the radical is by itself on the left side, so I square each side, so I end up with 5n equals 100. So I divide by 5, and I end up with n equals 20. So now let's try this back into my original equation. So I put my n back in of 20, so I end up with 5 times 20, which is 100, which gives me 23 on this side, and that is not the same thing. So it is an extraneous solution. And since that was the only one that we found, this equation has no solution. So now here are some for you to try. Especially go back and make sure that you can see if they're extraneous solutions or not, or what we need to do to find those. Okay, so now here's kind of our real world problem. So the period p in seconds of a pendulum, now a pendulum, remember, is just like a swinging rope, is given by this function, p equals 2 pi times the square root of L over 32, where L is the pendulum length in feet. So a pendulum has a period of 4 seconds. Is this pendulum twice as long as a pendulum with a period of 2 seconds? Explain your reasoning. So the first thing we have to do is we have to figure out what I'm doing. Okay, so I was given the two different periods and I'm asked to compare them. So I know that p is the period that I'm talking about. So I'm going to substitute in 2 and 4 for that p value and solve for L and compare. So I go ahead and I write out my function, and then I substitute my p's, right? I add a p of 2 and a p of 4, and then I divide each side by 2 pi because I want to get the radical all by itself. And then I can simplify, and we always want to leave things as fractions as long as we can. So now that I have the radicals by themselves, I go ahead and square each side to simplify. And when I'm squaring this left side, I have 1 squared over pi squared, right? And here I squared the numerator and I squared the denominator. Now to get this L by itself, I multiply each side by 32. And now I can use my calculator, right? Because I'm just asked to compare them. So I use my calculator and come up with my different lengths. So no, the pendulum with a period of 4 seconds is 4 times longer than the pendulum with a period of 2 seconds, right? And we were asked if it was double since I doubled the period, but in reality the length is 4 times longer. And I found that out by just simply following my same steps that I've done. So now here is what I want you to look at. Look at the equation that we just used for this last one and see if you can find the length of the pendulum that has a period of 2.5 seconds. So now we're going to look back at our learning targets. First thing was to solve radical equations. Now the first step in solving these equations is always to get the radical all by itself. Then we looked at our solutions to identify any extraneous solutions. And remember that those extraneous solutions are solutions that don't actually work if you plug it back into the original equation. Then we looked at a real-life problem involving radical equations. So now that we've done these learning targets, go ahead and work on your homework for 10.3.